Okay, so following along from the other video, we were at this step here where we were now looking at the change in volume of tank 2, the change in height over the change in time. This formula here should look similar to what you got in your notes from one of the lectures. And so back at it, we're solving for those coefficients that were given in B as A21, A22, and B2. So that's where we're at. Again, as the limit is approaching infinity, the change in height is going to be 0. So it's 0 now. And I wanted to point out, well, we'll get there in a second for C. But ignore the circles for now. 1 over A2 R12 times H1 infinity plus, this is essentially the equation. You'll notice that there's a 0 over here. It's all equal to 0. So from this, the constants that you get for A21 is those values. And as you can see where those come from, directly from there. For B2, I know a lot of you are confused about, you're like, well, there is no flow rate for this equation. There's no constant F1 over here. And we could probably do some work to get an F1 to show up here. But in my understanding of this problem, it's irrelevant. So let's just say that B2 is 0 and it solves it. If B2 is 0, it solves any confusion as to why it's asking for an F1. I do believe that you could rewrite the formula and have an F1 there, and you might actually have a B2 in that case. But this formula that I have, I'm pretty certain it's accurate, and I think this is the one we want to use. So let's move on to step C. So step C, this is where you're going to start manipulating those two formulas that you just derived. For the first formula, this is in regards to tank 1, necessarily the change in height of tank 1. We've already taken out the derivative here. If you look, this formula is going to look very similar to this formula right here, which is change in height over change in time, 1 plus h1 over 2. Remember, change in height over change in time as the limit approaches infinity is 0. So we've just excluded it altogether out of this formula. If you multiply everything in this formula by a1, you get rid of a1 completely, and now we don't have to work with the area. And that's what I've done here. So you'll see area is no longer there, and that's because we multiplied every one of these by a1, and that's algebraically allowed to do. Don't worry about that. And now for the second tank, we want to also try and figure out how can we rewrite this formula without area. We're just trying to simplify it, get it as simple as possible. Well, if you notice, I circled the area and all of these. Okay, I missed it there. Let's multiply everything in this equation by a2. This is a separate equation. If you multiply this by a2, it's 0. This by a2, it's just 1 over r1, r2, or r1, 2. And this by a2 gets rid of a2, this by a2 gets rid of a2, and this by a2 leaves you with 0 still. And that's where this second formula comes from. We just multiplied everything by a2, and now we have, let me see if I can get it wide enough so you can see where both come. This value here directly came from this here. This value here is a distribution of h2 infinity into these two terms. So this one is this term, and this one is this term. And you do want to separate those. You'll see in a second why. So now you have these two equations that represent your system, and we've gotten rid of the area altogether, which I think is important. I don't know that you definitely need to do it, but it's going to make it a lot easier for you. So let's just sum these two formulas together and create a third formula out of that. So if you sum this together, these two values will cancel out. So a little helpful hint, we can cancel these out. And now if you sum this value here, 1 over r12, with this value here, 1 over r12, h2 infinity, these two cancel out. So we can cancel that and cancel that. Now we're just left with h2, 1 over r2 h2 infinity is equal to 0. Well, let's rewrite that. Oh, wait. This f1 comes down, remember, because it's you're summing it. So this f1 plus 0 leaves you with f1. So that's where this f1 comes from. And then we multiply this r2 over to the other side, and that's where this r2 comes from. So now h2 infinity is equal to that f1 times this r2. And everything else canceled out. Looks pretty simple, and you're liking it, I'm sure. Let's move on. We've got this value here. Now we're going to use this. We're plugging this in for h2 here, so we can get h1 in terms of just these coefficients. So we plugged in f1r2 here into that equation. Once you solve, you can get h1 of infinity is equal to f1 r12 plus r2. And that's it. You've got h2 of infinity and h1 of infinity in terms of those coefficients, which is exactly what they ask you to do in C. Now, the last part they ask you is, do the initial values of the tank affect your results? And you can just look at these formulas and go, no, there is no initial value of a tank here, and there's no initial value of a tank here. So it doesn't matter. I don't care what heights were in the tank originally. This result is only dependent on the flow rate in. See that? Because these R2s, those are all going to be relatively constant, so to speak. I mean, they're constant coefficients, so they are constant. But what they describe, maybe not be. But yeah, so the answer is no. That doesn't matter what the initial values are, whether they're empty or not. Your steady state value is going to be the same, based on how I understand this problem. So let's move on. We're now into this page here, in D, where it's giving you some initial values. Down here, and you can see the initial values I wrote out. It's just plug and play. We have h2 infinity, that formula there. So let's plug and play, and we find out. And so this is how you kind of know if you got it right. Your units will start canceling, and you'll get a unit that accurately describes whatever you're looking for. So we're looking at for the height of the water after infinite time has passed, so to speak. The steady state value of the height of the water, well, 5 feet cubed per minute times the rate, which if you remember, the rate was described as 3 feet per feet cubed per minute. So that extra per there helps you out. That's what you need. So you have the initial height, where are we? 5 feet is the flow rate in, 5 feet cubed per minute times 1 foot per foot cubed per minute. And this is h2, remember, we're doing h2 first because it's easier. So h2 infinity leaves you with 5 feet because these two units cancel out. Isn't that nice? So that's always an indication that you're doing something right when your units are canceling properly. And then we have h1 of infinity is equal to 5 times 3 plus 1 is equal to 20 feet. Remember, we got h1 of infinity. This formula is coming directly from what we just derived here. h1 of infinity is equal to f1 times r12 plus r2. And f1 is constant. It was given as a constant. So no matter what time it is, we don't care whether it's in infinite time or it just started, it's always going to be that 5 feet cubed per minute because they said it was constant. So that's another part of this that you need to understand. Now, here's another fundamental understanding of the problem. You don't really need to do a lot of this solving here to get this flow rate out. You were given that flow rate in is equal to 5 feet, and it's constant. So you could look back at a problem a while ago, or an equation a while ago, which represented the system as the change in volume over the change in height. If I can just find that real quick. I think this is actually a pretty important bit of information that I'm going to pass on, if I can find it. I don't know that I can find it. Oh, I'm looking at the wrong book, that's why. This one is what I need. Here. So you were given this formula, if you remember it, change in volume over the change in time is equal to F1 minus FO. Well, at steady state, this is 0. So 0 is equal to a constant 5 minus FO. Well, you know FO has to be 5, right? The flow out has to be 5. If this is 0 and this is 5, flow rate out just has to be 5. But let's use the equations that we already just determined in other manners. So that was kind of a common sense solution. This is like the analytical solution. We have this equation, flow rate out is equal to the height at time t minus the height of tank 2 at time t divided by R12. Well, we were given from the equation, what we just determined, that height at infinity is equal to 20 feet, and height of tank 2 at infinity is equal to 5 feet, so 20 minus 5, and then R12 is 3 feet per feet cubed per minute. I just showed this. If you were to rework these units here, and instead of doing this division by feet divided by feet cubed per minute, multiply the entire thing by the reciprocal, you'll end up with feet cubed per minute on top and feet on bottom. And this unit here will cancel out this unit here. And so what you'll be left with is 15, that's coming from 20 minus 5, divided by 3 is equal to 5 feet cubed per minute. That's the only unit left. Hey, guess rate, we're describing flow rate. It should be 5 feet, it should be feet cubed per minute. So again, we got the units right. And look at that, it's 5. Just like we predicted, it had to be 5. Oh, do we want to predict what F2 is going to be? Well, we can look at the same equation. The change in volume of tank 2 over the change in time is equal to the flow out minus the flow, or FO, which is technically the flow in for tank 2, and F2, which is the flow out for tank 2. Well, we know that from what we just determined that the flow out is 5 feet. Well, we can assume that again it's going to be 5 feet for F2. You can do the analytical solution using H2 and saying, hey, it's 5 feet, which we have 5 feet divided by the rate 2, which is 1, and you'll get the same solution. So sometimes it's nice to have the common sense solutions to compare with your analytical solutions. Just a little helpful hint there. And finally, E, because of the way we solve this, you don't have to do any analytical analysis anymore because we removed all of the area. So repeat part D with A2 equal to 75 feet. No, we're not going to do that because we don't have to. Nothing's going to change. Nothing changes. Area of tank has no effect on steady state value. And that's important that you write area has no effect on steady state value because the area of the tank is going to have an effect on how long it takes to reach that steady state value. But it won't affect the actual steady state value, which is kind of interesting. Excuse me. For F, they just changed one of the values. After everything you just watched, you should be able to get through F without any help. And then now let's move to the last page. This is for G. So what you have here is FOs, what they're asking. So this is part of the problem is sometimes we'll read these questions and you're like, I'm not really sure what you want. Suppose tank 1 initially holds 10 feet of liquid. Suppose tank 2 has 4 feet. Find the initial rates of change. What's the initial rates of change? What are you asking for? What they're asking for is the change in volume over the change in time of both tanks. So the dV1 over dt and the dV2 over dt is what they're asking for. So what you're going to want to use to determine that first is let's find the flow rate out at the initial value of 0. And we have an equation for that. Flow rate out at time t, which is going to be 0, is h1, height 1 of time t, which is the initial value. So this is the initial flow rate out with the initial height of tank 1 minus the initial height of tank 2 divided by that R12, which you remember where that equation comes from. And same for F2, it's the initial value of the height of tank 2 divided by R2. So So you get those values there, 3 feet, 4 feet. Hopefully you understand where that came from. So now let's look at the change in volume of tank 1 over the change in time. Remember, F1 is constant, so initially it's going to be 5 feet cubed per minute, and FO, we just determined up here, is 3 feet cubed per minute. So your rate of change for tank 1 is equal to 2 feet cubed per minute. It's just 5 minus 3. Pretty simple, right? Do the same thing for the change in volume of tank 2. And you'll get a negative value. So really think about it. I'm not going to give you this one, but really think about what a negative value would represent in this system. What you're assuming is positive and what you're assuming is negative, because that tells you exactly what's happening in the system. The fact that that's negative, it gives you directional information. And then H, I'm not totally sure how to answer this. H, I don't know exactly why, but I don't know why, but I feel that there's no way that the height of tank 2 would exceed the level of the height of tank 1, mostly because in the steady state values, H2 is going to be less than H1, and that the fact that the flow rate out of tank 1 can never exceed the flow rate into tank 1, just based on how the equation unfolds. So given that information, I can't see why tank 2 could start filling up faster than tank 1 is, just because the flow rate into tank 2 is never going to exceed the flow rate into tank 1. That's kind of how I understood that. So I don't know if that's true, but hopefully that helps you kind of figure out. And if I'm wrong, please tell me. And then finally, this is pretty simple. But it does go down to the fundamentals of how we got to the equation in the first place. How does the model change if there's a separate flow going into the top of tank 2? So now we have this additional flow coming into this tank. Well, it doesn't change a whole lot, actually. You might think it would, but it really doesn't. The only thing you should change is the change in volume for tank 2. The change in volume for tank 2 is now going to be the flow rate in coming from tank 1, which is FO, the flow rate in that we just mentioned, F3, minus the flow rate out. It all seems pretty common sense, so hopefully that makes sense to you. I don't know if he wants you to derive all of the equations over again now that you have F3. In my opinion, it's unnecessary once you've proven that you can do it up here, because it's gonna follow a similar path in the method that you would take to achieve those values. So hopefully that helped you out, and that's it. Okay.